Okay, so next thing I want to talk about is enhancements made for async compute in this generation. Okay, so async compute. So async compute is one of the cool new features in DirectX 12. It's basically based on the observation that again, if you think about sort of the old school graphics, right? It was basically draw one thing, draw another thing, draw a third thing, chunk, one after the other, right? But graphics workloads are different than that these days, right? You'll often have, well, ultimately you might be arriving at the same point in terms of drawing a common picture, but you're getting there with multiple independent work that doesn't necessarily have to serialize on itself, right? So so the workload itself is asynchronous now. The question is, what benefits could that, knowing that, what benefits could you get out of that, right? There's a couple of benefits. So one is the observation of sometimes these individual workloads aren't using the GPU as efficiently as they could all by themselves. If you take these two workloads, run them together, they'll actually, instead of one after the other, let's say that takes 2x time to run them together, maybe it'll be like 1.8x time or something like that. It'll be somewhat faster than that. So overlapping is one of the ideas, right, for async compute. The other idea is sometimes you have workloads that are more of a real-time nature, right? So like asynchronous time warp, for example, for VR, right? You're doing your rendering. So another workload has to come in and do some stuff, or audio, like VR audio, which we talked about yesterday. The audio and the graphics workloads are asynchronous to each other, and you want to be able to make sure that one gets to go when it needs to go and can get out of the machine. So those are sort of the kind of things you want to do with async compute. And applications, physics is an application. You've got the game engine, is going to get onto the GPU to do physics work. And then it's going to get off and you do rendering or post-processing. Maybe you're doing post-processing compute, and then you're doing some rendering as well. And then VR, I mentioned that as well. So there's lots of interesting applications for this. In Pascal, we made 3 major changes for async compute, and I'm going to go through those. Okay, so the first thing that we changed in Pascal is the way that we do our overlapping of work compared to Maxwell. So there is one way to overlap work is basically what I would call kind of a static partitioning type approach. In a static partitioning approach, you say, I'm going to do graphics and compute, and I'm going to set the machine up to be partitioned. So let's say 1/4 of the machine does compute, and 3/4 of the machine does graphics, let's say, right? So that'd be a static partitioning approach. So that approach will work well as long as the two workloads kind of finish in the same amount of time. Right? If they don't finish the same amount of time, which is this example here, if one of them sticks out, then you're actually going to have some dead time, because you partition the machine to do compute 25%, graphics 75%. Now the compute work is still going along, and if there's no more graphics work to do until that compute work finishes, you're gonna have dead time in the machine. So static partitioning requires you to sort of get that balancing right. And the challenge is, how do you know if that balance is right? We can look at an application, kind of get a feeling for what might work, but you kind of got to set it up right. And if the workload changes, then your balance isn't right. So that can basically take away from the upside you could get from doing overlap. So the change we made in Pascal is we have a static partitioning mode, which you can use if you want to get that sort of iron grid partitioning. We also now have a new dynamic mode. The dynamic mode, the driver can tell us kind of how it thinks it wants things to be set up. But if we see that work isn't coming in for a period of time, we'll say, maybe we should let things slosh around a little more, right? So in this example where you had graphics work and we said we think a good balance might be 25-75, but hey, there's no graphics work coming in here. Why don't we go let the compute work take over more of the machines? So basically now we can fill that in, and so you don't have that extra time at the end. So you can both get the benefit of the overlap in the beginning, and then in the end you can fill the whole machine up like you want. So that was the first change we made for async compute in this generation. Okay, and now we're going to go to a demo. So this is a demo of this is a demo basically of the example I gave with physics, right? So in this demo we have a sort of a fluid particle simulation running with all these colorful red, green, and blue balls here, and in that physics simulation, in the game engine is ultimately feeding the geometry, which then gets rendered in the scene. So you got the physics engine, and the game engine asynchronously running relative to the graphics. And with async off, we're doing about, I guess, 70 some, high 70s FPS running this demo. And then if we can turn, so you can see the fraps counter never left there. So can we turn async on now? Okay, now with async on, we've now gone up about 93 FPS, which I think is kind of 15, 20-ish% faster. And basically what's happening is that this physics workload by itself sometimes builds up the machine, but then when you have these fluids calculations, there's going to be a point at the end where there might not be as much compute work to do. And so you sort of have some dead time in the machine. And now we're rendering the graphics here with the shadows and the lighting and everything. We can actually overlap that graphics work with the compute work. And so now we're able to run more efficiently. So the overall workload runs better.
There's Async Compute. It's
OK, why don't we go back to the main slide deck here. Okay, cool, thank you. Okay, so that's talking about kind of the first aspect of async compute, which is the idea of running workloads, overlapping workloads to get more efficiency. And the other kind of workload is the more the real-time workload, right, where you want to get a workload on the machine and get it running very quickly. And we made two changes here, which I'll talk about. So this picture is talking about how preemption works in a design. And I'm actually going to start on the bottom, which is with compute, and then I'll go up to graphics. So at any given time when the GPU is running, what you have is you'll have a push buffer of all the so a push buffer is a bunch of commands that the driver or the game engine gives to us, right? Now in that push buffer, let's take the compute example. Push buffer might have a whole bunch of grids in it, right? So where a grid is a grid to go calculate like a blending, maybe a filtering of the scene or something like that, right? And then each grid has a whole bunch of threads in it. So at any given point in time in the machine, there actually is a huge amount of work stacked up because you can have one grid that has, say, thousands of threads, but then you could also have hundreds of grids. So now there's another 100x ratio or whatever, and then you could have hundreds of commands, each having grids. So you can have a lot of work in the machine, right? And if you want to preempt at that command push buffer level, you're going to have to drain all of that work out. So it's going to take a long time to do that, and you're not going to be able to sort of deterministically get a sense of when you get on the machine. So for compute, in Maxwell, we have the ability to preempt already at a thread level. So for compute, we could basically, it's okay that we have these, the white are basically commands we haven't started running yet. The white there is grids we haven't started running yet. We're running a grid. We're kind of halfway through running that grid. We can basically say we don't have to finish the whole grid. We'll stop here. We'll finish the threads that are running, then we'll get off the machine. So we preempted that thread boundary. So that's a much more deterministic preemption for compute versus if we had to flush at a higher level of design. That's what we had for compute. Now, for graphics, we didn't have that before, and no one has had that before. So for graphics, the equivalent would be you have a push buffer. The push buffer sends a whole bunch of triangles down, and all the triangles have pixels, right? And if you have, well, let's say if you have a big triangle, maybe the triangle has 1,000 pixels, and you have 1,000 triangles. That's a couple orders of magnitude, and then you have a push buffer could have a whole bunch of triangle strips with triangles in them. So you have a lot of work queued up. Graphics GPUs can't stop at a pixel level and preempt until now. So in previous generations, basically, you would have to flush out at some point higher up here. Let's say flush out your whole push buffer, flush out all your triangles in the design. So for graphics, depending on what the workload looks like, you can have a not undesirably non-deterministic time to flush the workload out. So the change we made in Pascal is we actually went through the whole pipeline all the way down to rasterizer. So the rasterizer, the setup engine, other things in the chip. And we basically gave them the ability to preempt, meaning they now can actually save their state off, right? So this is a challenge because in a graphics pipeline, you're not naturally having to save state, right? The pipeline is, the work kind of is flowing through, hey, I've got a triangle, okay, the triangle's gone, that sort of thing, right? And if you want to preempt, you have to basically know all that state and be able to go find it and save it off, basically where you were in the middle of your work. So the rasterizer is now going to say, I was processing triangle 27, and I was on pixel, I was on XY coordinate blah, right? And we'll say preempt. You'll say, okay, I'm going to stop at this point blah. I'm going to save off that I was in the middle of working on this triangle, and there's these other triangles behind me. I haven't gotten any of those yet. I'm going to save that information off. And then I'm going to get all that work off the machine, and then now I'm clean. Somebody else can come in now. I can do whatever I want to do. So that's that pixel level preemption. So we'll basically stop at the pixel level. We will drain out the pixel shaders. Pixel shaders typically aren't insanely long things, so draining that out is not too bad. And then as soon as that pixel shader is drained out, we can then preempt. And this preemption is very quick. It's less than 100 microsecond preemption. So because we now have both graphics and compute, we've sort of covered both of our bases here. So when you're doing a gaming workload and you want to get, like let's say you're doing rendering and an asynchronous time warp comes in for a VR display, right? Whether it's pixels that are running, graphics that's running, or compute that's running, you don't care what's running. You want to get that off the machine to go get that asynchronous time warp in and get it done. And you want to give it the whole machine and get it done as fast as you can, right? And whether it's graphics or compute running, the developer doesn't have to worry about, did I have too much work queued up and I'm not going to get on the machine quickly enough. So so fundamentally, that graphics script is about covering both of our bases there. So for these real-time workloads to get in no matter what's in the machine. So VR, asynchronous time warp, audio, other workloads like that. So, yeah. Yeah. Exposable through what? Sorry? Yeah. So the question is the preemption exposable through normal APIs? So it will be exposable through DirectX. I think I'm going to look to the side again here. We don't need to wait for the July one for that. Is that right, guys? Okay, let's just make a note to maybe we can put that in the deck. But it's definitely in the one that's coming out this summer. I think it should be supported in the one that's now. We'll check on that. And then I don't know about Vulkan, but I know for DirectX we're going to be exposed. Yeah. That's our description.
Is this in hardware or software?
This is in the hardware. It has to be in hardware. Yeah, I mean the rasterizer is a hardware unit. It has to know what state to hold it. Okay. Well, actually, why don't I take one more question, then let me, because I have one more thing here. So I take one more question, then I'll keep going. Yeah.
Was the demo you just showed, was that DirectX 11 or DirectX 12?
I don't know if that was I think it must have been DX12, right? No, it was DX11. Okay, DX11. Sorry. Okay.
One more.
Yeah.
Showed fraps.
Actually, let me keep going. I'll come back to you. Is that okay? Okay. All right. Okay. But wait, we're not done. So there's another feature we have, which actually those of you that followed our compute launch of P100 mentioned, which is instruction level for compute. So not only can we do thread level, we can also go down all the way to instruction level now. So what that means is that you can have these threads running, and then I just sort of drew a picture here. Give an instruction is sort of saying take these two registers, add them together, go put them in a new register. That's the sort of the lowest level operation of the graphics pipeline. Is at this instruction level. And with Pascal, we actually have the ability to preempt at an instruction level for compute. So you can basically have whatever you're doing, we say preempt, and we not only save where we were in the grid and which threads running, we also save for each individual thread where was it in its program and what is all the state that it had all its registers open. We can save all that off, write that out to memory, and then stop right there and go pick up something else. So this is particularly useful for once you get into more general compute workloads, right? Like I think it would be really great if people use GPUs for more pervasively in applications on the desktop, right? But then if you don't know what the workload is going to be, and you don't want maybe somebody writes a more general compute program that takes a long time to calculate, you don't want that screwing up your windows from dragging around, right? And so with instruction level compute preemption, we're able to take those workloads and preempt them basically just like a CPU does. We can just preempt at instruction level. There's no dependency on knowing kind of how long that's going to run to completion. So we also have this support, which is supported by CUDA specifically. So when you're running a CUDA program, you'll be able to get this benefit. This is not in the drivers right now, but this will be in the drivers, I think this summer, something like that. So, okay, so I think that's what I had on that. So I can take more questions now. So there was someone that was going to ask. Yeah, there you go. There you are. Okay, yeah, so he was next. Let me. Yeah.
Okay,
Yeah.
Can you pick up the job once it's been preempted at the point where you left it?
Yes, yeah. So yeah, when we come back where we finished, right? So we said at the last, like for example, for pixel level preempt for graphics, the last pixel was x37, y38. So now we can continue after that point. The same thing for compute.
So Johnny, do you have a variable stack, and is the stack on die, or is the stack in GTX memory, or is it in memory?
So when we're running a program, all the state, the registers, the stack, et cetera, is on die. When we preempt it, we'll move that off die. So it's kind of analogous to a CPU, except that we've got like 1,000 times as many threads running. So it's a challenging problem there. But that's what we do. Basically, we get all that state and move it off the chip.
And so you'd use the GDR memory preferably because that's faster?
Yes. Yeah. So yes, basically, we'll have a pool of memory that basically is there. So when we want to preempt, we can then go write that state off to that memory.
With these new preemption capabilities, is this pretty much everything that is desired now, or is there kind of still more control that you might want later, that you might develop later?
I feel right now it's pretty much what's desired, but I also want to learn from, these are a couple of big steps forward we're taking. I think we're going to learn, we've improved things by several orders of magnitude, so that's going to be better. And then we'll want to see where things go from here. And then on the compute side, instructional preemption, that is kind of in the speed of light. There's no more to go there. On the graphics side, you could go to instruction level on the graphics side. The challenge would be, that is even more of the pipeline you'd have to go through to do that. As things stand today, pixel shaders aren't like doing infinite loops and things like that. So it feels like that's kind of a good place to cut it. It's very efficient to drain those pixels to memory. They're kind of designed to kind of run pretty quickly, so that sort of feels like the right thing. But we want to go put this out there, have people use it, and we'll see. We'll learn from that. So, yeah. Okay. All right. Cool. Okay, so I just have an example here, related to VR here. So this basically is showing this, what does it mean? What is the effect of having different levels of preemption on behavior, right? So this is sort of one of the concepts in VR that some of the VR makers look at, is this idea of basically that you're doing your rendering, and then asynchronously you're going to do this thing called an asynchronous time warp, which basically the idea is that you, at the moment of the display refresh, for the VR display, you're going to want to take the current head position, and you take your last. So you had a frame that was rendered with a certain head. Let's say the person was looking over here, right? And you haven't finished rendering a new frame since then, but they know that your head has moved a little bit. So the idea of the asynchronous time warp is that you don't warp right away. You actually wait until just before display, and you take the latest position of the person's head, and you actually warp the image a little bit more to reflect that final position of the head. And the idea is you want to do that as late as possible, because the later you can do it, the more accurate you'll be relative to tracking the person's head motion, right? Now, it's very important that you don't do it too late, though, right? Because if you do it too late, now you're going to drop a frame. That's going to make people sick. You'll have done a bad thing instead of a good thing, basically, right? So the question is, when do you have to make that request, right? The earlier you make the request, the less goodness you're getting out of the asynchronous time warp idea. But if you don't make it early enough and you miss, then you're sad, right? So basically the idea is you have to think about, okay, how much time it's going to take. So I have a display refresh. That's that yellow line there, right? You're going to have to do the asynchronous time warp work. That's going to take a certain amount of time. But then there's going to be this uncertainty. So I'm going to have to make the request early. And the uncertainty, one of the things it's sort of related to is how quickly am I going to get the machine, right? So let's say I say it takes me 1 millisecond to do the time warp. If I ask it a millisecond and the GPU takes a millisecond to get me going, then I'm going to be stuck because I don't have any time left, right? So you put in this buffer based on the ability of the GPU to preempt quickly. And the basic idea with preemption is that if you can push that to limit, so you can basically tell the developer that we're able to preempt and respond to you very, very quickly, then they can basically make that request later. They don't need to have so much of a buffer as they would have had previously. So that's basically one example of how this occurs. Okay, so this is sort of kind of wrapping up the GPU section, and then I'm going to move on to other technologies that we had here. So at the end of the day, we talked a lot about craftsmanship. We're very proud of the craftsmanship of this design. We're very proud of the speed of this design, and we're proud of the cool new features in the design. If you compare versus a 980 to a 1080. If we had just taken 980 and said, hey, we got a new process technology, let's bring a new process technology, we would have gotten a good performance boost, right? Because it's lower powers, you can run it at higher clocks, things like that. We would have gotten some benefit from that. But the other things we did that I talked about today really gave us a very big benefit, a bigger benefit than the process that actually gave us. You know, the craftsmanship that got the clock speeds up, the new memory technologies, the memory compression in the core, and then of course for VR, with simultaneous multi-projection, we get a really big lift on top of that. So for VR, there's a huge leap forward, and almost all of that is based on the architectural improvements we made in the design. So you get a very big boost clock benefit. Clocks are up a lot, and the performance is also really great. So that's basically, and then today, what the user gets from all the work that we did here.